Okay, welcome PCS members and friends to our today's Tuesday PCS IBS seminar. It is our first regular seminar after New Year, so Happy New Year to everyone that hasn't attended our short seminars before. It is a great pleasure today to have Dr. Cheng-Ju Jacob Lin from Perimeter Institute, and I would like to invite our scientific host, Dario, to introduce our speaker. Please, Dario.
Yeah, thank you very much, Dylan. Yeah, it's a great pleasure to have today Cheng-Ju from Perimeter, but actually from Taiwan, because he's currently in Taiwan, so we don't have problems of time. So let me introduce Jacob's career. So he started his Bachelor of Science. He got his Bachelor in Taiwan, in National Taiwan University, which is probably the main university of Taiwan, if I remember correctly. After that, he moved for his PhD degree in Caltech, where he worked on many topics that are, let's say, in my interest. So I find them very interesting, which is quantum chaos, thermalization, pre-thermalization, many-body scars, and so on. Currently, after his PhD in 2019, he moved to Perimeter Institute, and is still continuing to work on these topics. And on top of that, he added another topic that I'm particularly, let's say, that I particularly like, which is Krylov complexity. And indeed, today he's going to talk about Krylov complexity of many-body localization, operator localization in Krylov basis. So Cheng-Ju, we are very happy to have you here, and let's start.
Yes. Hi. Hi, everyone. So yeah, my name is Cheng-Ju Lin, and then I usually go by Jacob. And thanks, Dario, for the kind introduction. And yeah, so today I'm going to tell you about this recent work that I did with a master student, Fabian. So we studied this Krylov complexity, and especially in the many-body localization system. And of course, that I will give you some more detailed introduction about this Krylov complexity and many-body localization. And if you have any questions, just feel free to interrupt me at any time, or you can also type in chat, but I'll see if I can have any additional time, and then I'll see. But I encourage you to just unmute yourself and then just ask me any questions if you have any. Yeah. So okay. Yeah, so yeah, again, like this work is actually done with this outstanding master student in PI, and then now he's actually moving to Germany in Max Planck for his PhD program. Right. So I'll actually start out by just say that I think actually as a condensed matter physicist, it's really lucky to do condensed matter physics in this generation. And actually, maybe even for a lot of the other fields of the physicists. The reason is that recently there's this development of quantum computation platform, and especially that recently we have these so-called NISQ devices, or these are some kind of prototype quantum computers. So because of the development of these devices, it actually motivates a lot of motivates a lot of interesting problems for us to look at the condensed matter physics in a different perspective, and especially it's about the quantum many-body dynamics. So in a more conventional condensed matter setting, that you usually will have some material, and then it's actually really hard to do anything that's really out of equilibrium, or doing any kind of experiment that's in about quantum dynamics. But due to these recent NISQ devices, that people actually started to really test some of the more fundamental ideas. So for example, the here that I mentioned about quantum chaos or quantum thermalization, actually there's already a lot of the experimental group that they're trying to program or even simulate these dynamics in these type of the NISQ devices. And in addition to these new like fundamental quantum chaos or thermalization ideas, that people also started to think about some different dynamical phenomenon that actually breaks the ergodicity, or kind of like a different string about like something that's not quantum chaos. So for example, one special type of the model is the integrable models, and then people also trying to study or simulate the dynamics of integrable models in these NISQ devices. And there's actually some other new phenomenon that's kind of unthinkable before the realization of these devices. For example, the many-body localization, or there's some theoretical proposal about Hilbert space fragmentation, and also these new dynamical phenomena. Quantum many-body scars was actually initially discovered, or kind of was a surprise in these Rydberg atom experiments. So you can see that a lot of the new exciting quantum many-body physics that's really motivated or inspired by this experimental realization. And actually, not only the experimental aspect that's really exciting, theoretical-wise, that the development of these devices also motivates us to look at the problem of quantum dynamics in a different perspective. And especially, actually, this is the perspective really motivated by these quantum information sciences. So especially, I want to mention, say, it's actually the perspective of entanglement and also complexity recently that a lot of people are really interested in. Especially I know a lot of local people in IBS that are really interested in this perspective. So kind of different from the usual condensed matter perspective is that a more conventional way that one wants to characterize the quantum many-body dynamics is by looking at some long-time hydrodynamics, or maybe even some transport properties of the system. But because of these QI motivated measure, that nowadays people are really interested in this entanglement and complexity perspective. So today I'm actually gonna tell you this work that we're basically trying to look at the complexity aspect about the dynamics of many-body localization, and which is actually kind of in a sense that we're trying to contrast or compare to the already studied system, which is the complexity of quantum chaos. So this will actually be the main thing of my work or my talk today. So I'll just pause a little bit, see if there's any questions so far. Yeah. Okay, so if not that, I'll just actually introduce and then set up by introduce you about this very specific way of looking at the complexity of some quantum dynamics problem. So the setup is like this. So typically that there are actually kind of two ways to look at the quantum dynamics. One is actually a more conventional and actually it's more relevant, maybe I would say more relevant experimental wise, which is that usually in these NISQ devices, the way that you do the experiment is that you prepare some initial state, and then you just let this initial state evolve with some engineered or simulated Hamiltonian or even some unitary circuit dynamics. So this is actually the dynamics in the Schrödinger picture, right? But because of some recent developments about quantum chaos, people are also starting to be interested to look at the quantum dynamics in the Heisenberg picture. And in particular, that people are trying to characterize how does an operator under the Heisenberg picture, how does it grow or how does it evolve? So, and actually this perspective is more suitable when you're really thinking about the system in some infinite temperature ensemble. So if you think about, okay, let us study with some initial operator O, and this is actually the Heisenberg evolution, O of t. And you can actually imagine that, okay, if I want to calculate, just a sec. If you want to calculate this quantity, then you can formally expand this quantity using the Taylor expansion. And then you will see that you will need to calculate the commutation relation between your Hamiltonian and your initial operator n times. So there's like a nested commutator here. So, okay, So so you want to study the Heisenberg evolution of the operator, or actually trying to characterize how does this operator evolve. And there are actually some already kind of popular way to look at or to characterize the operator growth problem. So the first quantity that it's actually quite popular these few years is actually this so-called out-of-time order correlators. And it was actually probably a long time ago, this is some quantity that used by Larkin and Ovshinnikov, that they were trying to characterize some quote-unquote quantum chaos in some superconducting system. But recently that people get interested mostly due to Alexei Kitaev, that he was trying to characterize some quantum gravity problem, especially if he studied the SYK model. So that's actually how it got interesting. I would say that from the condensed matter physicist point of view, that this quantity is actually interesting in the sense that it characterizes the operator growth in focusing on the space-time region. So for me, that if you look at this O of t, and then imagine that it was initially that you want to know some operator that's initialized on some site I. And then under the Heisenberg evolution, it will actually grow bigger in space and then in time. So the way to characterize how big of this operator is growing is by looking at the commutation relation of this O of t with respect to some V operator at some site J. So if the size of the operator O is big enough, then you would expect that this commutator, the magnitude of this commutator will be large, right? But if Vj is really far away from the size of this O of t, then you should expect that the commutator will be very small. So that's why I think this is actually something that's more focusing on the space-time growth of the operator. And also I should mention that why does this out-of-time order correlator it can be associated with the quantum chaos. So if you look at the classical chaos, that say butterfly effect basically tells you that if you change your initial condition a little bit, then you want to characterize how much of your trajectory in the phase space differ in time. So especially that this thing should grow exponentially in time if you are in a chaotic system. So this quantity, if you write it as a Poisson bracket, then actually this is actually the Q of t and then and your NP. So a very straightforward quantization is by promoting Q and P to an operator, and then the Poisson bracket into the commutator. So you see that this is basically this quantity, but you can just take the absolute value of square, and then that kind of cancels out the phase effect of the quantum mechanics. So that's why, in a sense, that this is like a quantum version of this quantity. So this is one pretty popular way to characterize the operator growth in the Heisenberg picture. Another very popular, actually maybe starting to get popular way of characterizing the operator growth in the Heisenberg picture is by this quantity called the operator entanglement entropy. So in a sense that, let me just schematically write the operator as Oj, and then you have this matrix that has the Kitt and Bra term. Now you just imagine that you have a quote unquote operator state, which is isomorphic to your operator. And then basically just by flipping your flipping your bra to a cat. So now at each side, you have actually 2 degrees of freedom. And then now you have an operator state O like this. So now since you have a state, which is a pure state, and you can actually just calculate the entanglement entropy using the way that you use to calculate the entanglement entropy of some state. And now that if you have this operator under this operator state correspondence, there are actually already some work that they're trying to characterize the growth of the operator entanglement entropy. So I think a rough result is that if you have a chaotic system, then the operator and entanglement entropy will grow linearly. While if you have an integrable model, then the operator entanglement entropy will grow logarithmically. Yeah. So these are already some way of characterizing the operator growth that people were already studying or used it a lot, and then in a lot of different systems. So today I'm going to be focusing on this new perspective of looking at this operator growth, and which is actually from the perspective of the Lanczos algorithm. So again, recall that to calculate the Heisenberg equation for motion, you can one way to calculate this is by expanding the Heisenberg equation of motion. Taylor expand this so that you will need to calculate the commutation relation of your Hamiltonian with your initial operator to the nth order. But now imagine that let's just usually when you do this Taylor expansion, then you usually will have to truncate your expansion at some n max, right? So if you summing up this term up to some n max, then you can see that this approximated operator will be living in this so-called Krylov space or Krylov subspace, which is spanned by this commutation relation of h to your O to the nth time. And this Krylov space is actually a pretty famous and then I would say kind of standard thing in a lot of the numerical method. And so one natural way is that can we find an orthonormal basis for this Krylov space? And then this is actually where the Lanczos algorithm comes in. So Lanczos algorithm basically gives you a way to generate a orthonormal basis for this Krylov space. So, and then this is actually the algorithm to generate that. So once you generate this orthonormal basis for this Krylov space, we can try to see, okay, then let me just use this orthonormal Krylov basis trying to express the Heisenberg evolution of the operator so that and now all the dynamics will just be encoded in the time-dependent coefficient in front of these spaces, right? And then if you plug in this O of t using this basis back into the Heisenberg equation of motion, then you will actually get the equation of motion, which will look like something on the right-hand side. And then these BNs are the so-called Lanczos coefficient, which is generated from this Lanczos algorithm. So the nice thing about this way of looking at this operator growth problem using this Lanczos basis is that this equation of motion under this Krylov basis looks like a single particle hopping problem on a semi-infinite chain with the Lanczos coefficient corresponding to your hopping amplitude. Okay, so you can already see that. So to visualize how the operator grow on this basis, basically to visualize how this single particle wave function initialized on the first side at t equals to 0. How does this particle wave function evolve in time? And then yeah. So from this perspective, that there's already some pretty natural way to motivate some of the so-called some of the complexity measures. So for example, one of the complexity measures that was originally proposed in this original paper by Daniel Parker et al. Is by looking at this. So remember that these ONs are the basis of the operator that's generated with using this Lanczos algorithm. But at higher order n, it will involve the nested commutator relation between h and your operator to the nth time. So in a sense that as the n increases, this ON will be more non-local or more complicated. So n is kind of like one way to quantify the degree of complexity. So you can kind of calculate some type of the mean complexity by taking the mean, basically measuring the mean of n of your operator. And so that's actually what they define this as the Krylov complexity. And in terms of this single particle hopping problem, this is actually just the mean position of your single particle wave function from that corresponding description that I just described. And there are actually also other people, say Rabinovich and his collaborators, that they also propose a different complexity measure that's called this Krylov entropy. So basically, it's a way of measuring how spread out this single particle wave function is. And I would actually say that really some way to really visualize the complexity or how the operator is growing is really just by looking at the amplitude of this single particle wave function, right? So if this single particle wave function is propagating to large n exponentially fast in time, which is the case for the chaotic system, then you can see that it will be really hard to use Lanczos coefficient to calculate the it will be really hard to use the Lanczos algorithm to calculate the Heisenberg evolution of the operator. But on the other hand, that if this phi n of t is really localized at small n, then you can imagine that, oh, that means that the Lanczos algorithm will probably be an efficient way to calculate the Heisenberg evolution of your operator. And spoiler alert, that's actually the case for the many-body localization system. Yeah. Right, and I want to mention something real quick is that this complexity measure might sound a little bit unphysical, and which is actually true because any complexity measure is really kind of problem dependent or even algorithm dependent. So in this case, that I would say this Krylov complexity is indeed a little bit artificial in the sense that you're really thinking about calculating the Heisenberg evolution using the Lanczos algorithm. But I also kind of want to mention that there is actually some physical aspect about this way of looking at the operator dynamics. So one thing that this formalism is really connected to is actually the this spectral function. So there's actually a quantity that people usually really are interested in the dynamics is actually this so-called autocorrelation function. And one can actually see that using this Lanczos formalism or Krylov basis, the autocorrelation function is really just the amplitude of your single particle wave function on the first side or the 0th side. The Fourier transformation of this autocorrelation function is usually what people call the spectral function. And one can actually easily calculate the spectral function by diagonalizing this single particle problem. And then you just sum up all the, so the spectral function will just be a whole bunch of delta functions. And then the EMs are the eigenvalues of this single particle problem, where the weight is just the overlap of your eigenfunction to your first site, the probability of that. Yeah. So I just want to mention that this is actually something that it could be actually quite physical. So before I finish the introduction part, I should mention that because I want to study the problem in many-body localization system to contrast the already known result for the chaotic system. Then what do we already know about this Krylov complexity for the quantum chaotic system? So in Daniel Parker, their original paper, they actually had a mathematical upper bound. So and they actually have a hypothesis. So in their paper that they hypothesize about they have a hypothesis, which is that the Lanczos coefficient in the chaotic system will grow as fast as possible. And in the if you have a local Hamiltonian, then actually they can show that there's actually an upper bound that you can obtain. So, and then in 1D, that they basically show that this Lanczos coefficient, or like the hopping amplitude in this corresponding single particle hopping problem, will grow linearly when the dimension is larger than 1. But if it's in 1D, then there's a logarithmic correction. So this is actually also, they have a numerical result for this chaotic line. They calculate that using the such that model. So if you have this Lanczos coefficient, then you can calculate the single particle wave function evolution, and then again calculate the mean position of that wave function as a function of the time, which is this Krylov complexity. So for this case, d larger than 1, the Krylov complexity actually grows exponentially fast, while for 1D that it's some stretched exponential. So what's kind of interesting is that there's actually a paper by one of the authors in this PRX paper that he actually had a mathematical result, which is that if you have a spin chain model like this, which is actually just an easy model, adding some longitudinal field, if you keep all the couplings positive, he could actually derive a lower bound of the asymptotic behavior of your Lanczos coefficient. So what's a little bit surprising is that the lower bound that he obtained is actually the same, at least for 1D, is actually the same as this one. So which means that for this model, if your coupling is all positive, then your Lanczos coefficient is pretty much guaranteed, is mathematically guaranteed to have this n log n asymptotic behavior. The special thing is that if you choose the hx and hz random enough, even though all positive, this model actually can be many-body localized, which means that somehow from this result, MBL and chaotic system, in terms of Lanczos coefficient, is not that different. So yeah, this is kind of a little bit surprising. So that's what a little bit kind of motivated us to really looking into this problem more carefully, and then trying to characterize more about the operator growth in this MBL system. Yeah, and I'll just stop a little bit and see if there's any question so far. Okay.
I have a question about this integrable many-body localization system you just described. Right. Is the problem that it is essentially integrable? And therefore, you wouldn't expect it to satisfy the upper bound?
Right. So it is integrable in a sense that it has macroscopically many conserved quantity. And so, right. So yeah. So in a sense, like probably you would probably expect that it should probably behave more like this type of the integrable model, say the Heisenberg model, and which that numerically they show that it should scale more like a square root n law. But this mathematical result kind of says that's actually not true, because they have a lower bound that's basically this behavior. And as I will show you that numerically that it is indeed this behavior. Yeah. And yeah.
Thank you. That's very interesting. Maybe we can discuss in the end this issue. It's actually something that was discussed in some high energy physics papers. So yeah, maybe we could talk in the end about that.
Yeah, no problem, definitely. Right. So yeah, and I actually do like to spend way more time I should in the introduction part, and the rest of the 15 minutes I'll it's enough for me to show you the result. So specifically that we want to look at the operator growth problem in the many-body localization system using this Lanczos algorithm perspective, or the Krylov complexity. And we actually take this model. So we consider this easy model. So without this HZ term, this is just the integrable model, the quantum easy model. But when you add this Z term, the longitudinal field, that it becomes a non-integrable. And especially that when you make the field random on each side, then when the randomness is strong enough, so each Hj is just a random number that's drawing from this uniform distribution from -h to h. So when the h is large enough, and here that when h is larger than 3 or even 4, then the system shows a behavior of many-body localization, which is which is shown by the level spacing statistics that we calculated here. Okay, so and also just to remind you a little bit that people were already look at the operator growth problem in the many-body localization, but they look at this problem using the out-of-time order correlator characterization, and then what they saw is that the operator growth in the MBL problem kind of has this logarithmic icon, which is in contrast to, say, the chaotic system or even the clean integrable system that the operator actually grows ballistically. So you actually do have a icon that's linear in time. People also look at the operator entanglement growth characterization for the operator growth, and they also saw that the operator entanglement in the MBL system grows logarithmically, which is similar to the clean integrable model, but in contrast to the chaotic model that it actually grows linearly in time. Okay, so just to remind you that that's what people already know about the Heisenberg evolution of MBL system. So here that we want to study this Krylov complexity. So first of all, it's just that, okay, we have this Hamiltonian, and then we can just have some initial operator, then we just use this Lanczos algorithm and then to generate the Lanczos coefficient and then see how they behave. So here that I showed you the result that we started with the operator of Z operator. So this is sigma Z operator on the first side, and then with a different strength of the disorder. So recall that when h is larger than 3 or 4, then the system actually is in the many-body localization phase. While when the h is smaller than 3, it's more or less in the ergodic or chaotic phase. So you can actually see that from this figure. We plotted this line, which is actually n divided by log n. For these two lines, that they're basically in the maybe h equals to 1 is a better representative of the ergodic phase. It is actually indeed that behaved as expected, that it has this n divided by log n behavior. But actually, you can see that for the data in the MBL phase, that they actually also shows this n divided by log n behavior, which is actually also consistent with what Cheng-Ju had in his paper. Also, by the way, that we are picking the disorder realizations so that technically his mathematical result doesn't apply to our case. But even so, we still observe the same behavior. But something very interesting that you can see here is that this is the disorder averaged Lanczos coefficient. When the h is in the MBL region, you actually see a very strong signal of this even odd modulation. But when you're in the ergodic case, it is just almost like a straight line. There's actually no showing of this even odd alteration. So that's something that kind of different in the MBL system, that even though the overall asymptotic behavior is still the same as the ergodic case, that we do see this even odd behavior. And something that I also want to mention is that we kind of expect that this n divided by log n and then the even odd alteration is something truly present in the thermodynamic limit. So first of all is that for these finite size systems, that for example that here that we calculate several different system sizes, that you do see that the Lanczos coefficient seems to saturate after some n. But as you can see that the starting point of the saturation does get delayed when you increase the system size. So we do expect that this growing, this n log n behavior growth is really present in the thermodynamic limit. And actually this is something that's pretty common in a lot of other different models, that the Lanczos coefficient kind of saturates due to the finite size effect. Yeah, and another thing that we also want to show is that here that we choose the starting operator as x using x or z or y, but we all see this even odd modulation behavior. So we kind of show that this even odd modulation in the Lanczos coefficient is not something due to the special choice of the operator. Yeah. And right. So
sorry, Jacob, I have a question. Yeah. I mean, you said that the asymptotic is the same for a chaotic system and this supposed to be MBL system. Asymptotic is the same, but we know that once you have Bn, essentially you have everything. I mean, the system is solved.
Yes.
So it must be that let's say the difference in the dynamics, the differences are completely controlled by this staggering between odd and even sides, right? Because
right. So that's one part.
But I mean, can you understand why precisely this staggering is causing the difference in the dynamics? How, I mean, how this staggering cause the differences in the dynamics? Do you understand that?
Yeah, this is actually a great question, but I kind of want to say that at first that when we saw this result, we also thought that, oh, maybe this even odd behavior is actually what's causing the dynamics that what's distinguishing the MBL and the ergodic case. But there's one caveat, which is that this is actually a result of disorder average. So to really understand the dynamics of the operator, we should look at the single disorder realization, right? So, but I agree with you that this is something that what does this even odd modulation
one thing that I find interesting is that I mean, these kind of modulations are pretty common when you study quench dynamics driven by MBL systems. I mean, they appear in many other quantities. So I'm wondering if this, I mean, I can show you maybe later in the discussion, I can show you a few other examples where in the dynamics you can see some kind of modulation. And I mean, we always thought, okay, this is a signal of MBL, but we never understood what was the cause. So maybe this kind, I mean, through Lanczos, one can figure out better what is going on. Yeah.
Yeah, I agree, but I'll say that I don't think we understand the cause of the even odd modulation that well, but we have some conjecture about what does this even odd modulation tells us about the spectral function. Yeah.
Okay.
What causes this is a little bit hard for us to tell. Yeah. But I think there's another special point that I want to point out about the behavior of the Lanczos coefficient is that actually there's in terms of the average of the Lanczos coefficient, you do see this even odd modulation. But when you look at the single realization of the Lanczos coefficient, as I'm showing here, that you actually see some erratic behavior, or I would say it's like a effective randomness in the Lanczos coefficient. But here I didn't show the result when you are in the ergodic phase. But when you're actually in the ergodic phase, that you do see for each individual disorder realization, the Lanczos coefficient is actually quite smooth. Yeah. But this is another thing that we observe in the MBL system. So from these observations, so one is this behavior of the even odd alteration, and then the other is actually this effective randomness in the Lanczos coefficient. We have a conjecture about the asymptotic behavior of the Lanczos coefficient in the MBL system. So this is our conjecture, which is that we conjecture that the overall asymptotic behavior will still have this n divided by log n behavior, but you will have possibly different slope for the even and odd branch, and then with some shift in the constant direction. So the important thing is that
let me be provocative, not provocative, but let's say, do you have any insights of how these coefficients could scale with the system size, could behave as a function of the system size?
Right. So that's why we kind of only take this part, which is unaffected by the system size. And so that's why I was trying to mention that the really finite size effect is really coming in this plateau part. And then for example, that we actually calculate some using a different algorithm that we calculate the Lanczos coefficient up to 31 system size. And then we also see the Lanczos coefficient is unaffected by the system size. So yeah, so we kind of expect that this part, yeah, this part is representative of thermodynamic limit, while this plateau part is really due to the finite size effect. Yeah. And of course, this n log n is kind of motivated by this mathematical result. So that's why we expect that, or we conjecture that asymptotically that it will have this behavior. But what's special is that the even and odd branch will possibly have different behavior. And also we included this gamma n term, which is basically the random on-site noise that we added to the Lanczos coefficient. So just to be more precise, that by this formula, we mean that for each disorder realization, you will have a given AE or CE or AO or CO that's possibly drawing from some unknown ensemble for each disorder realization. But then on top of this, for each disorder realization, for different n, you actually also have a random on-site noise. So that's our conjecture. Yeah. So of course, it is actually a little bit hard to really verify. But one thing that we did to kind of corroborate this conjecture is by looking at the statistical property of these AE, AO, CE, CO, and this gamma n. So what we did is that for each disorder realization of Bn, we take this part, which is from n equals to 10 to n equals to 40. Again, that we believe that this is the representative behavior for the thermodynamic limit. We take this part to fit this formula for the even and odd branch. And then this is the histogram of the AE and AEAO and CECO behavior after the fitting. So again, that if these these parameters are really drawing from some ensemble that's independent identical distribution, then by the central, is that central limit theory? Yeah, by some statistical theory, that you should expect that they will look like a Gaussian, which is actually what we observe here. And also, of course, that you can kind of estimate the variance and the mean of this unknown distribution from these parameters. So after fitting this, that we take the difference of our fit and the real data, which was trying to characterize this gamma n part. Then that's what we plotted here in this great histogram. And again, you see that they do show a very beautiful Gaussian. So that kind of indirectly, at least that's supporting our conjecture that this gamma n is just some random on-site noise drawing from some unknown distribution, or at least that you can view that as this way. Of course, that there's no way to figure out, almost no way to figure out what was the real underlying distribution, but this is just some statistical result. Yeah.
Yeah, please, Ruth, go.
I wanted to ask, how many coefficients did you compute? How many Lanczos coefficients were you compute?
Oh, we used 1,000 disorder realizations. Yeah. Is that your question?
She's asking how many n.
Oh,
right?
How many? Okay, so here that we can calculate up to 1,000. But again, that because the rest of the Lanczos coefficients are corrupted, basically affected by the finite size effect. So we only took n from 10 to 40 to do this fitting. Yeah. So yeah. And the nice thing about this Lanczos algorithm is that a lot of people, they, again, like actually like 50 years ago, people were already using this Lanczos coefficient, Lanczos algorithm to calculate a lot of, say, especially a spectral function. One special thing that they do is that they try to extrapolate the behavior of the Lanczos coefficient to thermodynamic limit using various methods. Yeah. So here that we're also trying to do the same thing. So then from the rest of the talk, I will actually for some reason I will present you two sets of the data. the one set is I will call the unextrapolated data, which is that I just use the Lanczos coefficient from n equals to 0 to n equals to 40, which is truncated n max, but still not affected by the finite size effect. And then there's another set of the data that I will show that's by using this extrapolation that we take this real data for each disorder realization from n equals to 0 to 40, and then we patch the rest of the data generated using this conjectured formula, and that's what I will call the extrapolated data. So
Jacob, I would have another question that probably you already told me, but I missed. So, I mean, do I understand correctly? Suppose that AE and AO are equal, and CE and CO are equal. We will be in the chaotic case.
Yeah, a chaotic case, that's the case. Yes.
Okay. Now the question is, now AE and AO must be functions of the system size, but also of small n. Am I right?
No, AE and
because
AO are
because somehow you showed that, let's say, the two slopes are mostly different for small n, and for large n they tend to agree. Am I right?
No. So these parameters are independent of n.
Okay, but do they function of the system size or not? What do you believe?
I believe it doesn't, and again, the reason is that we think the main effect of system size is in this in this plateau. Yeah. So okay. Yeah, it's kind of from a little bit.
Okay, during the discussion, I will explain you why I'm focusing so much on this point.
Sure. Yeah.
Okay.
Yeah, but I just a quick word that the reason why I believe that is that we actually looking at, again, just by this figure, that we're looking at different system sizes, and then we do see that before this onset of plateau, these Lanczos data that they basically overlap with each other.
This is the point that I don't understand of this plot. I mean, you see, the difference between AE and AO looks more pronounced for small n, while going to 25 looks to disappear. That's why I was thinking that AE and AO should be function also small n. I mean, close to 0, the discrepancy is larger.
Yeah, I see. So I would say that maybe there's a way to suggest more sophisticated conjecture for the formula, but yeah, this is just our maybe a more less sophisticated conjecture. Yeah.
Okay. Thanks.
Yeah, but indeed, like we were like, I agree with you that because you have to guess something, and of course that you want to make a guess that so that it doesn't affect the other properties that you want to talk about. So one thing that we did try to check is that, okay, does this guess or extrapolated data how much does it affect the behavior of the spectral function? So we calculate, again, like using this Lanczos coefficient, that you can calculate the spectral function, which is the Fourier transformation of the autocorrelation function. And one result is that when you have this n log n behavior, then at high frequency, the spectral function will decay exponentially. So here, because we only have the numerical result, and then if you want to calculate the spectral function, you will just get a whole bunch of delta functions, right? So the custom way to resolve this is actually by considering this cumulated spectral function. So you just integrate the spectral function, and you extrapolate the smooth part, and then you try to take the derivative of that smooth part to recover the smooth behavior of the spectral function. Hopefully that is representative of the thermodynamic limit. So when we look at the cumulated spectral function, we indeed observe that at high frequency that it decays exponentially. So when you take the derivative of omega, you expect that the spectral function decays exponentially. Another important behavior that we saw is that in the MBL phase using this Lanczos coefficient, both from the extrapolated or the unextrapolated data, we actually do see that there is a presence of the delta function at zero frequency for the spectral function, which is actually a hallmark of the MBL system, because the presence of this A means that the autocorrelation function will decay to A, which is non-zero at infinite time. And because of then this is actually one feature of MBL, because the system doesn't thermalize. If the system thermalized, then you would expect that the autocorrelation function will decay to zero at infinite temperature at infinite time. Yeah. So this thing is something that also kind of suggests that our extrapolation scheme is reasonable because it doesn't affect the high frequency behavior and the zero frequency presence of the delta function. We also try to extract a little bit about the singularity behavior of the spectral function at low frequency, and we kind of get this behavior, but I would say that this might not be that I don't know, like yeah, it's not that easy to get, and so but we still try to extrapolate some singular behavior, but it's kind of hard to say if this is like the true behavior at low frequency, right? So so once we have this unextrapolated data and the extrapolated data, then you can again just calculate the dynamics of this single particle problem, right? And then calculate the mean position of your wave function. That's the Krylov complexity. So what we found is actually that you can see that the x-axis is actually the time, but in the logarithmic scale. So even in an exponentially long time, we actually observe that the Krylov complexity seems to be bounded, or at least the average of the Krylov complexity. And what one really wants to pay a little bit attention is that the value of the mean position is actually really low compared to this artificial truncation of the Krylov order. Okay, so of course that ideally that you want the truncation order to go to infinite, but due to the numerical constraint that you have to truncate it at some point. But when you increase this truncation, we do see that, say, truncation 500, 800, and 1,000, the mean CK doesn't really change too much. And also we suspect that this fluctuation at really long time is due to some finite Nmax effect. Yeah, I can probably explain more, but that's what we suspect. And something you can actually even visualize more is actually how does this wave function, single particle wave function amplitude look like? So here that we just calculate the evolution of the wave function, but with these different times. And noted that the time is actually exponentially long. So for the figure on the left-hand side, this is calculated from the unextrapolated data. So for each disorder realization, we calculate this wave function, and then we take the disorder average of the amplitude afterward. You can see that even after exponentially long time, it's really localized at around the first site. And the right-hand side is using this extrapolated data. So we have the real data, and then we extrapolated the data using our conjectured formula. And you can still see that even at exponentially long time, that the wave function is still localized around the first site. So which is actually kind of a very different behavior compared to, for say, the chaotic case. So for the chaotic case, that you actually see the wave function will propagating out. There will be a wave packet that's propagating to the large N exponentially fast. Yeah, but here that you actually see that the wave function is localized. Right. So I'll just pause a little bit. I still have 5 minutes, right?
Sorry.
Oh, sorry.
Jacob, can I just ask about this figure? What can you say about this localization in more detail? I mean, it doesn't look to me very exponentially like localized, or.
Yeah, I am I want to say exponentially localized, but I don't have an analytical argument to support this. Because sometimes in 1D, it could be some weird stretched behavior. So, and especially this is a little bit different from the typical, say, Anderson localization. So usually in Anderson localization, that, or here you're actually talking about the off-diagonal disorder, right? Or because you only have hopping. And in this case, that you expect that the typical Anderson localization with off-diagonal disorder is that your Bn doesn't grow in n, but here it's a little bit hard to say. So I agree that this is just something that we observe numerically, and then I don't have very good analytical argument, especially from the understanding, like the, yeah, it seems like it feels like some problem that can be related to the typical Anderson localization problem, or like the off-diagonal Anderson localization, but it turns out it's not, because of the Bn, the Lanczos coefficient behavior is not constant with random noise. It's really something that grows almost linearly. So I don't have a good analytical result. Yeah.
Okay. Thank you.
Jacob, I have a question. So is this the complete size of the Hilbert space is 1,000, or is it just part of the Hilbert space?
No. So here that we on the left hand side we truncate the Lanczos order to 40, and then the right hand side we truncate the Lanczos order to 1,000. But the Bn after 40 is patched with this conjectured formula. And here I actually didn't show you that what happens for the real data, which is that, for example, if you take just this Lanczos behavior, but you keep this plateau, which is coming from the finite size effect by, for example, that we actually calculate this, that when we keep this up to 1,000, then what do we see? So in that case, that we actually still see something almost like exponentially localized when the n is less than 50, which is the onset of the plateau in Bn. But afterwards, the wave function kind of stay in a constant amplitude. Yeah.
And this is done for which sites?
Oh, sorry, say it again.
Which system sites are you showing this?
So for all these figures, the original spin chain has system size 13.
I see.
Yeah.
Okay.
Yeah. So
for disorder 3, right?
Sorry, what was the question again?
Disorder 3, right? The H, I mean the H of the distribution is 3,
no,
right?
So, sorry, the disorder is 7. So it's kind of
7, okay.
Deep,
so that is not disorder, okay.
Yeah, it's kind of deep in the MBL phase. Yeah, sorry,
okay.
I didn't mention that. Yeah.
Jacob, you can take 5 more minutes. Yeah.
Okay. Yeah, I should be okay, because I think the physical bit part is the more interesting part, and also just to compare with this operator growth, but you really use the physical bit. We also studied the operator growth starting from this so-called L bit, and then under this MBL phenomenological model. And I'm sorry that I will not be able to explain more about what is this MBL phenomenological model. So yeah, if you already know MBL, then you would know this. But roughly speaking, is that there's a way to diagonalize this many-body localization model, and after diagonalize the model, you obtain a phenomenological Hamiltonian, which will just looks like whole bunch of tau z operators, and then they kind of interact with each other. So this is a totally classical model, but these tau z's are related to the original sigma z operator by some finite depth circuit, and then they have some special profile that's exponentially localized. And then if you have this phenomenological model, the parameters will usually decay exponentially in terms of the interaction distance, yeah, and also the number of the L bits that's interacting with each other. So we also studied that we use this MBL phenomenological model, and then starting with the tau x as our initial operator, and then just trying to calculate the Lanczos coefficient and also the behavior of the Krylov complexity. And here that we actually saw that we still see this behavior of the even odd branch, but instead of growing linearly, that they basically just stay constant asymptotically. Yeah. So the left-hand side is the Lanczos coefficient upon disorder average, and the right-hand side is just the behavior for several disorder realization. And again, that the blue ones are the odd branch, and then the red ones are the even branch. So, and once you have this BN thing, and then here that we don't worry about the finite size effect, and so we just take this BN up to 4,000 and calculate the Krylov complexity. And actually what we get is that here that the Krylov complexity actually grows linearly in time. And when you look at the particle propagation, or the single particle wave function propagating as a function of time, it actually propagates to large N. It looks like there's a wave with a sharp wavefront, and then it just propagates almost linearly in time towards large N. Yeah. So this is something that's in contrast to that physical MBL model that you started with the physical bit. Yeah. So
well, wait. I'm super confused. Yeah, I mean, sorry. The phenomenological model should be the model describing the true MBL phase. Now you're saying in the true MBL phase things is propagating?
Yes. So I think that the reason is that because you take a different operator, so that your Lanczos basis is, so you generate different Lanczos basis, so you have different BN. So of course so you're doing the same operator growth problem by using a different basis, so they could have different behavior. Yeah. So of course that ideally the physical, well, yeah, ideally the full Heisenberg picture evolution should be the same. They're just being conjugated by some unitary transformation, right? But the Lanczos the Krylov bases are actually different because of the choice of the operator, or because of the algorithm and the choice of the operator. Yeah.
Oh, okay.
Yeah, and sorry that I'm flashing a little bit, and basically really just to quickly summarize that, I think something that's a bit unexpected for us is that in the MBL case that this Krylov complexity is actually bounded, or the single particle hopping problem is actually localized, as at least when you initialize on the first side. But we know that in the ergodic case, this wave function or this single particle hopping problem should be delocalized, and actually the wave function will propagating out exponentially fast. So is there any way to connect this single particle localization delocalization transition to the MBL localization delocalization transition? So that could be something interesting. Another interesting thing is that from this result that we actually see that the Krylov or Lanczos algorithm could be one way to efficiently simulate the operator dynamics for the MBL system. So can we use this result and then come up with some other more efficient classical algorithm to study the MBL dynamics? But I want to say one caveat is that even though it looks like the Lanczos algorithm seems to be efficient for MBL, but to construct the Lanczos basis, these operators are still exponentially expensive. So to be able to capitalize this result, one have to think of some clever way to efficiently generate this Krylov basis, even in MBL system. Yeah, and finally that we see that in the quantum chaotic case that everything should be hard, exponentially hard, and especially that even if you want to use Lanczos coefficient to calculate the Lanczos algorithm to calculate the Heisenberg evolution for the chaotic system, that it's exponentially difficult. But for MBL, it seems to be more efficient. And how much does this carry on to other different type of dynamical systems or non-thermalizing systems? Yeah, that would be interesting to know more. And yeah, thank you for your attention.
Thank you, Jacob, for this very interesting talk. Let us thank Jacob. Oops. I have some technical issues. Here. Okay, and we have time for questions. So perhaps let me start. You were, as also you have written here, so spectral function, it's interesting, right? Because it can be experimentally probed. So are there any kind of comparisons with some experiments?
Oh, yeah, not that I know of. So I think probably part of the reason is that most of the MBL experiment that people are doing are on this, I don't know, cold atom systems. And then actually in that case, that it's easier to measure something in the real-time domain other than the frequency domain. Yeah, so, but I guess maybe in a sense that you can measure something in real time and then just post-processing doing Fourier transformation by hand. But I don't know. At least I'm not aware of any experiment that they're really measuring spectral function already, or like maybe measuring something and then calculate the spectral function yet. Yeah.
Mm-hmm. So not yet, because the real space is simpler.
Yeah, but I think maybe one feature, some feature could be tailed, which is that at the infinite time, does the autocorrelation function goes to 0 or not? And then what's the behavior when the autocorrelation function goes to infinite? Say, does it decay exponentially or in polynomially? Then that would translate to the low frequency behavior for the spectral function, right? So that could potentially be something measurable. Yeah. But I think the challenge for experiment is that usually these cold-atom experiments is that the coherence time is the bottleneck. So it's a bit hard for them to see something that's truly on time. Yeah.
Mm-hmm. Okay, thank you. Sergey has a question.
Yeah, could you go back one slide, please?
Oh, this one?
No, the other one. Yeah, this one. Yes. So
I
didn't really catch. No. The one. Yes, the Krylov complexity one. So I didn't catch really the details of the comment of Dario, but I sensed there was some interesting issue here where you say that you somehow changed some bases, and then you even in deep in some assumed MBL phase, you see some kind of propagation. Can you maybe explain that again in a bit more detail?
Yeah, definitely. Yeah. So technically, if you really have a truly MBL system, then you can imagine that I have a edge MBL, and then I have a unitary that I need to diagonalize this Hamiltonian, right? So when you diagonalize the Hamiltonian, it actually brings your brings your MBL Hamiltonian into this form. And then this tau z is related to the sigma z with the same unitary, but just conjugated with that. So in terms of operator dynamics, the Heisenberg picture is as if that everything is just conjugated by this unitary, right? So if you truly have an MBL system with the phenomenological model, then the operator dynamics will technically be the same, just conjugated by this unitary. But the reason why the Krylov complexity behavior could be different is because now we are just a little bit artificially trying to look at the operator Heisenberg evolution using this Krylov basis. But the Krylov basis using the phenomenological model and using the MBL model, when you start with L bit and P bit, they actually generate different bases. Yeah, I think that's probably the zeroth order answer, so that they just behave differently, just because you use a different basis to expand your Heisenberg evolution. Yeah.
Mm-hmm. Is that somehow related to something which is called ergodicity of integrable systems, or ergodicity on tori? So basically, that you choose, so to say, you somehow measure your observables using, let me put it that way. You actually don't measure the proper observables. This is what can happen when you look at the ergodicity on a torus, for instance. You simply measure something which is related to the angles and not to the actions which are frozen. Is that something similar here, or is that?
It might be. It sounds like conceptually similar in the sense that probably what you were referring is that in the classical dynamics that you could measure the dynamics in different variables, and here is kind of similarly, but instead of different variables, you're using different bases. I guess, yeah.
Thank you.
I mean, Jacob, can I paraphrase? Let's say paraphrase the question and the answer by saying that, I mean, once you go in this basis, tau 0x in the original basis is actually an horrible operator, and its evolution can look chaotic, although the model is not. I mean, in terms of the original operator.
Right,
no, but no, it's still local. It should be still quasi-local, right?
Well, it doesn't have to, because you choose the basis differently, right? So it's not quite chaotic yet because the wave function doesn't propagating out exponentially fast, but it's delocalized, but delocalized slower than the chaotic case. But I always say just it's because you use a different basis, to look at the dynamics.
Maybe it's related to what we observed in the paper, that large operators can delocalize well also in presence of integrable dynamics. Maybe it's the same thing.
Yeah.
Okay. Yeah. Maybe we can chat.
Yeah. And in a sense, like in this phenomenological model, the operator dynamics is really defacing in some sense. So one could probably even understand the dynamics by only keeping maybe two terms, and one could actually see that the operators like kind of defaces, and but somehow because you deface, then you sorry, maybe I should just say that it's just due to the choice of the basis.
Okay. Thanks.
Okay. Ruth has a question also.
Yes, thank you. So you're saying that in this case, the Krylov complexity does not saturate at the lower value. Is that essentially your result?
Yeah. So I kind of flashed a little bit. So you here that you kind of see that at long enough time that it seems like CK kind of saturates here, but that's just due to this artificial truncation of the MX. Numerically, you have to truncate it at some point. But when you increase the truncation of your Krylov order, you do see that this growth, the Krylov complexity kind of grows even more in time. And actually physically that you can actually kind of understand why this happens from this behavior on the right-hand side. So what really happens is that the wave function initially initial on the first side, but as time evolves, that it will becomes like almost like a square wave and then propagating to large n. So at some time that when you have an artificial truncation of mx, let's say at 2000, then your wave function can only propagate up to that point, right? So this is the time that when the Krylov complexity saturate. But of course, that when you increase the mx, then the wave function can propagate more or indefinitely, and so that's why we think that the Krylov complexity should grow linearly in time indefinitely. If you really have a truly thermodynamic limit, and mx goes to infinite. Mx goes to infinite limit. Yeah.
I see. So you're saying you don't see any exponential phase, growth phase for Krylov complexity in this case.
That's right. Yeah.
I see. Thanks a lot. So in some sense, you're saying that. I mean, going back to Altman's paper, Parker and Kao and collaborators, they were claiming that in chaotic systems, Krylov complexity would increase exponentially, at least in a thermodynamic limit.
Right.
Whereas, actually, okay, so, but they don't see any kind of linear growth of Krylov complexity, do they?
No. So
you're saying it's special somehow to these MBL systems, this kind
right,
of
and it's because of it's special to the phenomenological model. And actually, I don't remember, but maybe one of the maybe for free model, it probably also Krylov complexity probably also grows linearly, but I actually don't remember. Yeah, a lot of the result for integrable model and free model, they only calculate the BEM behavior. They actually didn't calculate the Krylov complexity. Yeah.
Yes, I agree. Yes, indeed. Thank you. Thanks a lot.
No problem.
Okay. Do we have any other questions from the audience? It seems not. So let us thank Jacob again. And thank you all for joining. With this, we conclude our today's